So you guys can see my screen?
Yes, sir.
Right there.
Let me remind you. Okay, so as I mentioned, this is CE08383, analysis and design of steel frames. The name is a little bit confusing because it may imply that you're only going to work on steel frames. This class, the name could be design of steel structures. But we are going under name change for next semester and following semester, so we're going to be design of steel structures. And majority of the class will be steel frames, but will be also other members that we will be designing. As I mentioned, my name is Islam Mantawi. I am a PE. I know the guys are pushed to take all your EIT or FE exams, and along the way, as a civil engineer, it's really important to get your PE license, so you got to certify your design and drawings, right? My email address is mantawi@rowan.edu. I don't know if you guys know my office. My office is on the second floor of Rowan Hall, room 230. I'm pretty sure most of you know Doug Cleary, and his office is at the end of the second floor. So I'm kind of in the middle between Jagdish and some other mechanical faculty. So today we will have the introduction. This is the first lecture. As I mentioned, I'm going to limit it to just 1 hour today for the first section or lecture. This is pretty much snapshot from our syllabus. So the class is CE08383. My name is Islam Mantawi. I just mentioned where I'm located. Feel free to reach out by emails or stop by. I do have what's called open door policy, which means that if you see me in my office and my door is open, feel free to stop anytime to ask questions. Also, I do have my office hours on Monday between 2 and 5 p.m. The best way to get hold of me is to email me to get appointment, and you can do it either WebEx or in person. The class location, hopefully starting next Monday, will be Rowan Hall, Engineering Hall, room 320 from 11 to 12:15. And on Wednesdays, we're going to be Engineering Hall 320 and both sessions also, which is good. So always go for Engineering Hall for a steel class, but we will start at 8 to 9:15 for the first session and 15-minute break, and another session from 9:30 to 10:45. Some of you might ask, will we take 3 lectures every week for this class? I may say yes. However, it's going to be at least 2 lectures for the main topics and 1 lecture to work in class for project that we will assign through the semester. As you can see today, we have shorter version. We have not in-person classes, and I really believe in in-person class and communication through in-person teaching. So starting from next week, hopefully we'll go back to the in-class work. And also we missed, as I mentioned, Monday because the semester started yesterday. As I mentioned, communication could be should be using my email address, as you also received already from me. The easy for me to put the subject as CE08383 in the subject and follow what your question about, like homework 1 or quiz 1, etc. I'm not sure if you guys received my email related to the manual. I get some confirmation from you that the manual was ordered and hopefully will come soon. Will not need the manual today, but hopefully if you have it next week will be perfect. Do you guys have any question related to the manuals? We will focus on the latest edition of 16, which is just published like a few months ago. If you have any question, hopefully you'll have it I have it with me today, but it doesn't make any sense to display it. But starting from next week, we will almost use it every lecture. So please make sure that you have it with you. I'm not sure if even you receive it, you will see that this manual is like the reference for you for any design steel structure from connection to members. So very much we will navigate throughout the lecture. The textbook, I usually don't push students to get the textbook, and my slide could be comprehensive. However, anyone interested to know more about the class, I'm aligning my lectures with this textbook, which is Structural Steel Design by McElmore, and the 6th editions. So the very recent one. I talked to a person, and they actually give me an option that you guys can rent a book online version for $45 per semester. So if you are interested, I can send you the link so you can print the book, have an online access. Any questions so far before we go to the class objectives? If not, I will resume. So the objective of this class, actually, you'll have opportunity. Let me try to put a pointer here. So you'll have opportunity in this class to comprehend fundamental and concepts related to steel design. This is a very big goal for civil engineering student. So you will be able to understand the theory, logic behind, and design equations used to select sections. And you're also going to be introduced to what is a steel properties, understanding the manufacturing process, and structure properties and characteristics. The student will be able to understand different types, loads, and load combination, which we'll start today in the second session. And we will also be able to have basic analysis and design for tension, compression, flexion members. The student will be able to understand buckling modes like local buckling, flexure, torsional, and torsion flexure buckling. The course will have also emphasis on limit state design and allowable stresses, load resistance factor design, along with the steel connections for both bolted and welded connections. So basically, this class will be divided to design members like tension member, compression member, or flexure members, and how to connect those members together. For example, you design the column. Column is most likely to be under either compression or compression and flexure. You will design it, and you will design a beam, and you have to connect the two pieces together. So that's why you need to understand how to connect them. So that's why we cover bolted and welded connections. We will also focus on our work with what is engineering's ethical responsibility. This class, this is the grading of the class. We have a lot of work to be done. We first will have, last actually we'll have the final exam weighted as 25%. So it's not majority of 40% or 50% as other classes. We have what's called quiz exams. Quiz exams include the midterm exam plus in-class quizzes. We will have a very very long semester project where you guys can apply each learning outcomes to design a building that's like 4-story or 5-story or 6-story. This project will help you a lot in your capstone design. Your homework will be 20%. We'll have a small project where you're going to be doing iconic structures, like research on iconic structure and come up with some literature and what is spark your interest in the structure. And also we'll have a strict attendance policy. For today, I see majority of you already in the class, but starting in-person class, we will be doing the attendance very strictly. I just want to mention that the class project the 20% is a group projects. So you can have a group of 3 or 4 of you, total of 7 or 8 groups. So the group will be 3 or 4 students, and you will be work together collaboratively on the design. The lower bound for A minus is 90, for B minus is 80, for C minus is 70. Hopefully no one will go beyond that to B's, but this is very much the grading and scoring. Here is just a course overview, what we'll be covering. The first lecture and second lecture are both today, virtually. And today we have introduction to the class and also a very quick review on structure analysis. I'm pretty sure this class actually steel design is it has a prerequisite on structured analysis. So we're gonna just fresh your mind with the shear and moment signs, load, how to draw shear moment diagrams, and etc. And this will be hopefully the first part of the first lecture, and will be end at 9 a.m. today. The second lecture, which is from 9:15 to 10:15, will be on specification, loading, load combination, and method of designs. We're also gonna cover next Monday the rest of this topic, which is the tributary area, and we will also be able maybe to start talking about the steel as material, advantages, disadvantages, what section you are using, and what materials you are using as grades for steel. So very much this is the first what I call topic 0, which is the prerequisite, and topic 1 is the introduction. As you can see here, I have it in blocks because the topics are like 7 or 8 blocks, and I can be interchangeable. So I can teach, for example, after tension members, I can teach connections, or I can choose to teach other block. So the first block is topic number 2. We will know how to design tension member and do analysis for tension members. I'm targeting hopefully 5 lectures to do that. The second block will be topic number 3, compression member analysis and design, and I'm targeting 4 lectures to finish it. They're going to be a long 8 or 9 lectures on flexure design. This will be, hopefully, we target end of February to finish the core of it. Your midterm exam will be on Monday, March 4th. Sorry, the review of the midterm will be Monday, March 4th. Your midterm exam will be the first lecture on Wednesday, March 6th. I make it intentionally so you avoid having your midterm after the spring break, so you can enjoy a little bit your spring break. After spring break is a week of March 11 to 15, no classes. You'll have a project day on March 18 right after you're back from the spring break. We will be doing for 5 lectures how to design bolt connections, and for 3 lectures how to do welded connections. And this hopefully will end by April 3rd. This is pretty much the core of the course, but I have actually a project day on April 8th. And I have what's so-called mock-up days, which if we do have any delay in the course, because I took a couple more lectures on one topic, because sometimes I actually work with you and either speed up or slow down my progress to ensure that you get the material information. So basically I put that day because in April 10, I'm planning to travel to UK for a conference. So I will adjust my schedule accordingly. There is a topic number 7, which is design of what's called beam columns. Beam columns is the members that carry both axial and bending moments, and I have it for 4 lectures, and we have the project delivery and reviews toward the end, and the final is the week of April 29. Do you guys have any questions with the outline before we start our review of topic number 0, WhatsApp hold? Any questions, guys? Okay, so I hope everything is clear. So this is actually going to be 30 minutes of interactive discussion between me and you on a review of a structure analysis. So this is a basic example where you have a simply supported beam, you have hinge and roller, and the beam is 12 feet span. You have a concentrated load of 600 pounds placed 4 feet away from point A. And this is your global coordinate, X and Y. For this one, I'm asking you to calculate the reactions. So I really want you guys to get engaged with me here. So do you guys remember from structure analysis, what is the equilibrium equations? I may start calling on you if you guys don't volunteer. Go, Rob.
The equations are sum of forces in y equals 0, sum of forces in x, and the sum of moments are equal to 0 as well.
Yeah, this is great. So this is for 2D structures or planar structures. So summation of Fx, all the forces is, summation of them is 0. Summation of y, is also 0. Summation of moment at any point or at any support should be also, at any point should be 0. So this is what's called the equilibrium equation. In this case, we will be using x to the right as positive. So this is a positive x. And y upward is, I don't know why the arrows are overshooting. So this is going to be a positive, and anti-clockwise for moment is positive as signs. So if I ask you guys how to get the reaction RA at support A, what should we be doing? Can someone volunteer or still remember? Adam, can you go ahead and, yeah.
Sum of moments at A.
So sum of moment at A equal to what?
0.
0, correct? And if you take the moment around A for RA, it's already 0, right? Because the distance is 0, right? So RA times 0, right? And if you take the moment around A for the force 600 pounds, can you add the moment here? Will be 600, right? And this is anti-clockwise, so 600, oh my God, pounds. Let me try something else. Times 4, correct? So 600 times 4. However, RB is going to be rotating, actually 600 times 4 is rotating clockwise, so this should be minus, not plus. And RB around A is going to rotate counterclockwise, so it's going to be plus RB times 12 equal to 0, right? This is 0, so you don't have it, RA times 0. You have 600 times 4 plus RB times 12. This will give you RB equal 200 pounds, right? Any question, guys, for this? You just take the moment around A, or 600 times 4 in negative, RB times 12 is positive. So this is your first RB. Can anyone else tell me how to get RA? This value here? Anyone?
Sum of forces in the Y.
This is clever because you can now use sum of forces at Y. This is the sum of forces, right? Equal to what? 0, right? So you will have downward negative 600. Upward is both plus RA plus RB, correct? Equals 0. RB is here, 200. So if you solve for that, RA will be 400, correct? So this is pretty much how to get the reaction for the simply supported beam with a load displaced 4 feet from the support as 600 pounds. Any questions? Okay, let's go to the next one. It's the same example, but I'm asking you to calculate the shear diagram. You know here RA was 400 and RB was 200. Can anyone volunteer to draw with me the shear diagram? Yes. So the shear diagram, what you need to do is you start with the beam, either left or right. If the forces are going upward, it will be positive. If the force is going downward, you have to move negative. So start at A, we have 400 going up, right? So it's upward, so you go up and we write 400, correct? As you move, there is no forces you will experience, so you will have flat line until just before, here, to be honest, until just before 4 feet away from the support, right? This is feet. And once you meet at point C here, you will have force of 600. So you have to move from positive 400 down 600. So you're going to get negative 200, right? And after that, you continue passing C as flat line because there is no forces between C and B. And after that, you meet RB, which is 200, and you go up 200. So this is 200. Above the line, you can use it as positive. Below, it can be negative. Any questions so far? I know it's very hard not seeing any of you and explain, but if you have any question, please raise your hand or just unmute yourself. So this is how we're going to do for the shear diagram. I'm going to move forward with drawing the moment diagram. So if you have the shear diagram from before, it's 400 flat. Oh my God, this is not good for the shear diagram. Let's redraw it. 400 flat, go down 200 flat, and back to 200. So we got 400 here, positive, and negative here, 200. Okay. Do you remember how to get the moment diagram from the shear diagram? The moment is integration of the shear, correct? So if you want to calculate the moment at this point, right? you can get the area of this block. The area is, this block is rectangular, that is 4 feet length and 400 pound in shear. So if you want to draw the beam again, to draw the bending moment diagram, you will have 400 times 4, the area of this piece is 400 times 4. It gives you 1,600 pounds per foot. Pound foot. And you will actually add it here. And since you are flat line here, the integration will be an inclined line, a sloped line. And from the left side, it's also 0 here, as you know. So this is going to be your moment diagram, and the value here will be 1,600. Oh my God, 1600. So any questions? It's very much easy one. You just go flat line, inclined line, and go back to another line. This is not a line, and this is going to be 1,600. Okay, so let's go to the next one. The next one is a uniform load, 75 pounds, acting at 8 feet length, a uniform load from point A, the hinge, and the span is 12 inches. 12 feet, sorry. Do you guys know how to solve this problem? I'll wait for a couple minutes. Hopefully you guys can start maybe calculating the reactions for me. I'm gonna call up on you guys, okay, in 3-4 minutes. Tyler, Manning, so if you have this problem, what you're gonna be your first thinking?
I would probably take a moment about A.
Yeah, same procedure, right? But this is a uniform load, right? It's 75 pounds per foot, right? So the resultant of this one will be 75 times 8, correct?
Yeah.
And this can be, you can just put it as dotted line here. It's not an actual force, but this could be 600, right? I don't know why my 600 is really awful here. 600, okay? Pound as concentrated load at the middle, right? As equivalent to this uniform load, just equivalent with reaction, right? If you take the moment around A, right? Equal to 0. You will have what forces? Can you follow up with me the numbers here? Tyler?
Yeah, you want the numbers you said?
Yeah, so it's gonna be what? 600,
Yeah,
right?
times 4.
And 4, because it's reactive in the middle, right? It would be
Yeah.
counterclockwise or clockwise?
That'll be clockwise.
It's gonna be negative, right?
Yeah.
So negative 600 times what? Times 4.
Yep.
You already RA is not, RA is 0, right? The moment from RA is 0 because there is no distance, right?
Yeah.
And from RB will be what distance you're gonna be using?
12.
Okay, so plus 12 times RB, right?
Yeah.
And this should be equal
0.
0. That give you RB is equal 200, correct?
Yeah.
Right? And you have to put the pounds here. And anyone else help me getting the RA? Maybe Luca.
I did some of the forces in the Y after getting RB to get RA.
Okay. And how much you got?
400
400,
pounds.
right? So 400 upward, right?
Yes.
So you got 400 here. Sorry, 200 here. 200 and 400 here. Very similar to the first one, right? Even the load is different. This is 400, right? Because the resultant is the same at the same location too. So I'm gonna move forward to draw the shear diagram. You know this reaction is 200, right? And this is 400. Oh my God, goodness here. What's going on with my mouth? 400, right? I'm gonna call on maybe Julia.
We're gonna start off by
0.
increasing the
Yeah,
value of RA, which was
400.
400, and then you're going to diagonally go down by 75 pounds per foot, so 75 times 8, 600. So diagonally, and then you do cross the x-axis there, then you're going to be at negative 200. You're
Okay,
going
so
to horizontally draw the line to the next endpoint and then increase it by the final
yeah. So
200.
this is exactly. So you start with 400 because your reaction is upward, right?
Yeah,
And every 1 foot you have to decrease by
by 75. So it's 600 minus
It's
600 going diagonally.
So yes, so you're gonna move from 400 to 600, and you're gonna draw a line that will cross here, right? At 0. And since you don't have forces beyond this uniform load, you will have a flat line and go back to 200, right? And this will be the positive side, and this is going to be the negative side. Okay. Thank you. This is great. So this could be a little bit tricky. We draw the shear diagram. You got the 600. You guys are gonna boast for you the hand calculation in a better format than today, because the mouse is not helping me. It's 200 here, and there's also 200 there, and a flat line, and a uniform line here. And this number is 4 feet, and this number is 8 feet, right? So if I want to talk, maybe call maybe Liza, you'll be here. Are you here?
Yes.
Yeah, sorry. So in order to get the moment, you always get the integration of the shear diagram, right?
Right.
And I don't know if you guys remember, at 0 shear, it will be your maximum moment, correct? So at this point, if you want to calculate the shear value, what you're gonna be doing?
You're going to be finding the area of the shear and plotting that as the moment.
On the left side, right?
Right.
So this is positive. So it's gonna be, do you know the area for this shear diagram? The area will be
It's,
the area of triangle, right?
yes.
So
It's
it
1/2
is,
times 600 times that X value.
yes, X value. Are we able to get the X value?
Yes.
If you know this is Actually, this is not 600, this is 400, right? So if this 400 and this is 200, can we get x? Yes, right? Because we know this distance is 8. If you do the interpolation to get this one, you're gonna get 400, right? Divided by x should be 200 equal 200 divided by this distance, right?
Mhm.
And this distance is what? It's
Is it
8 minus
X?
x. So can we solve for x?
Yeah.
So if you solve for x for this example, hopefully it will be 2/3 of 8, which is, I think, 5.33. So this distance 5.33. So you got 400 times 5.33. Can anyone calculate for me this 5.33 times 400 times half? I think it's going to be around 1066 or 1067.
1066.
Yeah. Okay, so this is the value here, right? If I want to get the value here, what should I do? I should also get the area from the left or from the right. Which one is easier? From the left or from the right? Can anyone volunteer or should I call on you guys? Okay. Mike? I don't know if you have yeah, Mike? I don't hear you. Ryan? Ryan, can you?
Yeah.
Yeah. So if I take the area, the easier to take it from the right, right? It's either from all the right or all the left, right? So what's the area from the right? The value is 200, right? And the distance is 4, right? So what's the area? I don't know if I lost you or not, but the area is 200 times 4, and it's a rectangular section. So area, so this is 800, and it's gonna be the value here, right? You just need to draw the lines now. Every time you have a flat shear, your integration will be inclined line for a moment. This is not inclined line, but and if you have an inclined line, you should be going back to the second order parabola. It's going to be parabola, right? But this is going to be your diagram. As I mentioned, I will be uploading the neat calculation for that for you shortly. This is a last example before we take our break. This is a beam, which is not a typical beam. This beam has no loads, but counterclockwise moment of 1,200 pound per foot acts 4 feet away. So same rules, right? Let me call on Rob, not Rob, but Shemin. Or Zach. Is Zach here? I think he's here.
Hello?
Yeah. Yeah, so the same concept, right? To solve for reactions RB, what should we do? Take the moment around.
Can you repeat that?
To
Sorry.
get the reaction at RB, what should we do?
Take the moment about A.
Yes. So if you take the moment around A, right? Take the moment around A and make it equal 0, right?
Mhm.
what is your moment, right? You take it around A, your moment here is given as 1200, correct?
Yeah.
So gonna be 1200 and it's counterclockwise, right? So it's what? Positive, correct?
Yeah.
And RB in this direction is upward, right? And it's going to also rotate counterclockwise, right?
Yep.
So RB is times it's positive 2.
Yep.
Times what?
Times 12.
12. And if you solve for that and make it equal 0, your RB will be negative, right?
Mm-hmm.
Sorry for that. RB is negative 100, right?
Yep.
What does it mean to have negative 100? Mean that your action upward should be actually what?
It should be going down.
Should be going down, and this should be
Good.
100, right?
Yep.
That's great. Same thing, Zach. Nick D.
Yes.
In order to get the reaction RA, what should we use? Summation of
Of the y-axis. In this case.
forces of the y-axis, right?
Mm-hmm.
So what force do you have? You have RA going up, right?
Mm-hmm. And then we have RB.
Negative going down, right?
Yeah.
Because going down, right? What's going to be your RA?
Our RA is going to be 100 going up.
Right. So this is actually funny because now we're going to have 100 going up, right? And 100 going down, and you don't have any uniform or concentrated load, just a moment. That will get you the balance, right? Okay, so this is good. For the shear diagram, we know this one is actually downward of 100. And this is upward of 100, right? Can anyone volunteer drawing the shear diagram for me? That should be easy one. Okay, Adam.
Go up 100 and then
Okay.
just go straight across and then go down.
Exactly. So go up 100 with a reaction, right? Move until you get the reaction going down, right? Correct? Thanks, Adam.
Yeah.
This is great. Yeah. I want to be like Flip, maybe. I want to choose virtually everyone. But I know if there's so many in the class. But if you solved before, feel free to say, okay, I solved if I called you twice. So, Rob, can you actually flip? Are you here?
Yeah, you can hear me?
Yes. So in order to get this diagram for moment, right? Let's go to the next one. So you have the shear diagram is constant line of 100, right? But you also have a moment that here act counterclockwise 1200, 4 feet away from what? From the support. Can you get me, and this is paused, right? Can you get me the moment at just before the application of the moment, the concentrated moment? It would be the area of the curve, correct? To the left, right?
So that would just be,
It would be 100 times 4, right?
yeah. So
And
400.
yeah, and in this case, you will have it upward, right? As 400, right?
Yes.
Oh my God, and this is 400, right? And passing this one, you can calculate from the right side, correct? going to be 100 times what?
100 times 8, so 800.
And opposite direction, correct?
Yeah, it goes down.
Okay, so this is exactly what will be your curve, right? 400 dropping what? To 800, right?
Yeah.
And the good news that the difference between them is what? Negative 800 and positive 400.
400.
No, it's a positive
Oh,
minus 800. They give you what?
1,200.
Yes, which is what?
The moment.
The moment itself. So I think I'm on time. This is 9 a.m. in the morning, and we finished the first topic 1-1. And I think if you guys can still hang on and just do like a walk break or bathroom break or even breakfast break, come back at 9:15. If you have any question, let me know now. I'm hanging on. Okay, so I hope that everyone is back. We're gonna start topic 1-2. Let me put everything ready here. So do you guys have any questions related to the first topic? If you have, just raise your hand and we can communicate if you have any questions. So it's pretty much review of a structural analysis, right? So the first homework you would expect to draw some bending moment diagram, shear diagram, and get reactions. So just to refresh, okay? So topic 1-2, we are gonna focus on specification, loading, and design methods. If I ask someone what we have done already, if I have a load, let's say this is the first problem that we solved, right? A beam, concentrated load of 600, right? And the reaction of 400 here and 200 there, right? And we're able to get the reaction. We drew the shear diagram and moment, right? So the shear was going up 400, flat and drop, sorry, flat and drop to 200, right? 200. And the moment was, if you recall, around 1600 this way. I don't know what's wrong with my pointer. If I ask you one question, you very much know how to get reaction, shear, and moment. However, if I ask you how this force came at the first place, right? Like the 600, did you guys get exposed on how to calculate forces on structures? I don't think so. In structural analysis, we give you set forces and you calculate reaction moment diagrams, right? So in this lecture, we will know how to get those forces into the structure. So we'll talk about specification, how we get load combination, and design methods. And let's say we get the force, you draw the moment, you know the maximum moment was 1600, right? And the shear was maximum of 400, right? This is pound, and the moment is pound-foot, correct? So this is due to the load that you have on your structure. So if you want to design your beam, what should I do? I should get a beam that can carry more than, just simply for now, more than 1600 pound-foot, and also can resist shear more than 400. It's very similar to any problem in life, right? If you have supply and demand, right? if your supply is more than your demand, right, life is good, right? If your supply is less and your demand is higher, you get problems, right? So in your design, you need to make sure that the girder capacity or the element capacity in shear and moment are higher than what experienced, right? In general, just a general design philosophy. If you have another example, if you have a traffic, right? If you have a road that can carry only one car and there is flux of cars going through this road, so the demand is more than capacity of the road, correct? So that's why you have downtime and you cannot reach to your place on time, right? So this is pretty much that how to get the loads on your structure. And after you get the load, you draw the moment and shear and design steel section that can carry more than the demand. As I mentioned, this is the most important booklet or handbook that you need to have throughout the class. Can you guys text me or not text me in the chat box? Can you tell me if you guys ordered it or and receive it, or ordered but not received? I just want to make sure that at least next time we meet, we will have it. So some of you got it, right? I actually ordered it, but didn't receive it myself. That's why I brought my grad student handbook. So hopefully it's coming for everyone. Anyone did not go ahead.
Can't see your screen, by the way.
Oh, I'm not sharing my screen.
Yeah.
Oh my God. Let me redo it then. So I did not share the screen. Okay. So you can see it now. Can you see the screen now?
Yeah.
Yeah.
We can see it.
So let me redo that one. So what I did before is, before the screen problem, I said you have a beam, right? And this beam has 600, whatever number of load here, 600, let's say 600. And you're able to get the reactions and draw the moment, right? And bending moment, you have the moment maximum was 1,600 pound per foot, pound foot. And the shear was 400 pounds, correct? In it, as I mentioned, the 600 here, actually, you don't know how to get it yet, right? In structure analysis, we just give you the loads, right? So in this class, you will understand how this number came from, okay? So this is the loading side, which we'll cover in this second lecture today. And after you get the moment and shear, you need to make sure that you have a cross section or a beam, steel or concrete. In next lecture, next semester or following year, you may get concrete design. It has to carry capacity more than the 1,600 pound foot or in moment and shear of 400 pound. And I gave you the example of the supply chain, an example of the traffic demand, right? So let's go here. And as I mentioned, this is the handbook that we're going to be using, the 16th edition. I'm pretty sure that you guys took advantage of the discount code AISC is offering. And trust me, since this is a very new manual, it's just they released it a few months ago, you will not get it cheaper elsewhere, okay? So throughout the class, we'll need to have it. We also recommend this book, but it is not mandatory to have it. We also we're going to be using ASCE 722 for the loading, okay? You are not required to purchase it or to borrow it from anyone. I'll be covering the basic of the loads from the slide. So hopefully you will not need to get ASE. I have a question. You guys familiar with ASE missions or not? Aside from, the concrete canoe or steel competition, any one of you knows what is ASE mission? Maybe I call on someone. Chris, maybe, or Adam.
I don't know.
Okay, that's a good answer. So ASE is American Society of Civil Engineering. So they serve few missions. One of them is the activity for the student to increase interest in civil engineering. And they also a publisher of journals, and they also a writer of specifications. So you can see here, this is a minimum design loads for building and other structures. So there are so many committees that meets in a voluntary basis and periodically to update the loading based on research done and other means of communications. They also are advocates for your politicians. So they also hold a lot of meetings with politicians, try to push safety of building and other structures, especially tall building and seismic and wind research. So this is pretty much the ASE. AISC is American Institute of Steel Construction. They focus on the designs, okay? So the AISC is mainly on the loading side. It's the AISC Steel Construction Manual mainly on the design side. And if you take concrete next semester, you will see that ACI is also the design side of reinforced concrete structures. So let's talk about loadings, okay? If there is different type of loading, so you can see here the numbers, number one. The first type of load, we call it dead load. Any one of you know why we call it dead load? Maybe Robert?
The dead load never changes.
Yeah, it's something you cannot move, right? Amplitude doesn't change or location, right? So it's permanent load on your structure. Do you know example of dead loads? If you have a beam that carries slab, right? So the slab weight is the own weight of the slab is a dead load, right? You cannot come tomorrow and ship like 1 inch from a slab, right? The girder weight is always constant, permanent. So the own weight of elements are what's called dead loads, right? You also have some element that is called superimposed loads, which pretty much like floor finishes, walls, permanent walls, like a wall in your houses, right? The ceiling, the HVAC system, the cladding, the stuff that is kind of permanent, no one tomorrow is gonna move it from place to another. If you have partitions, the partition is, if it's not fixed partition, is not counted as dead load. If you move the partition to gain a space, that will be counted as a different load type. So dead load, just basics, is any load in your structure that's permanent and you cannot move, correct? If I ask you, is your furniture in your house or the table in your classroom is dead load or live load or not dead load? Anyone can volunteer? Or maybe answer if you don't wanna, maybe in the chat.
Dead.
So the table is dead load. How many of you think it's a dead load? Raise your hand, maybe. So Julian and Joe Mecken, yeah. Can anyone say it's dead or live or not dead? I don't see anyone talking actually. Joseph.
Yeah, I think it's a dead load just because like there's nothing else changing on it. It's just a table or like a couch or whatever.
Yeah, but have you ever moved the table from a place to another?
Yeah,
So it moved the location, right?
yeah, yeah.
So any change in the loading location amplitude, right, is gonna be not dead load, okay? The only thing is someone can think about dead load is like, it's not like a speaking one, like the table is not speaking, but what I'm saying is today you can have boxes in your table, right? And you can have it empty. It can be in your living room, it can be in your, you know, bedroom. It can be in, like, for example, you go to a classroom, we can take all the table and rearrange another setup, right? So those are changing loads, right? Those considered not dead load, it considered as form of live load because it changed the magnitude or change frequency or location, right? Also, if you have equipment and you know it's fixed service equipment like cranes or material handling system, those also considered a dead load. So anything that you think the load will move to one location to another or magnitude will change or frequency, that will not be a dead load. It will be more like a live load, okay? How to calculate the dead load is easy because if you have a slab, concrete slab, you know, concrete is unit weight is 150 pound per cubic feet. So for every cubic feet, if you draw a cube, right, of concrete, I know if some of you work on in our lab for casting, if you have 1 foot by 1 foot by 1 foot, and this is a concrete, reinforced concrete, the weight of this one is 150 pounds. So the unit weight of reinforced concrete is 150 pound per cubic feet. If you have similar block, but it's made of structural steel, the load is 492, and for simplicity, you can use it 490. Okay. And we have different numbers, like, for example, steel partition, movable steel partition, plaster and concrete, and this is actually pound per square foot, which is not pound per cubic foot, mean that if you have area, let's say you have your cladding or your flooring system, it's actually per area, okay? So every 1 foot by 1 foot will weigh 4 pounds. In this class, I want you to remember, stamp it in the back of your brain, those two numbers, the 150 pound per cubic feet and the 490 pound per cubic feet for reinforced concrete and steel, structural steel, respectively. Any questions? The second type of the load, we call it live loads. And the live loads, we have roof load and general live loads. So in order to get the live load values, you have two choices. The first choice is to use IBC. IBC stands for International Building Code, table 1607.1. This is for live load value, which is what at the ASE adapted at table 4.1. Here is the easy way in table 4.1 ASE CEI 722. Okay. This actually give you the functionality of your building and what is uniform live load will be. So if you have apartment building and you use a private room or corridor, you have a private room or corridor serving them, you use 40 pounds per square feet. What is PSF? If you have area of 1 foot by 1 foot, in this case, you will load this area by 40 pounds. Public room and corridor serving them, you will use 100. For office buildings, If you have lobby and first floor corridor, you have 100. Offices, 50. Corridor above the first floor, 80. Anyone can guess why in some cases our lobbies and corridors are 100, much higher than the regular offices or private rooms? Anyone can guess why it's higher? Chris or Colton or Julian, Mike, anyone can guess? Adam?
There's more traffic like going on.
Yeah, more people, right? If you have your classes today in person, right? How many people outside waiting for us to get out? Gonna be almost the entire class, right? Next class, right? So gonna be in these lobbies and corridors, you'll have a lot of traffic, as you mentioned, a lot of people waiting. That's why we get it from up to 100. Also, during emergency and evacuation, what do you see? You see elevator shutting down, right? You cannot use elevator. You always have to use stairways, right? And corridor will be very crowded. So that's why we have in the lobbies and the first floor corridors a higher load than in room and classes. So you have also classes for schools for 140, corridor above the first floor is 80, first floor corridor is 100, and a stairway and exit way is 100. So it's much higher load because you expect more of loading on those places, in these places. If you have storage warehouses, if it's light storage, if you look at going to, warehouses or Costco or whatever, you got like lightweight warehouses will be 125. If it's heavy, it's gonna be 250. If you have stores, retail, ground floor, upper floor, wholesales, those are gonna be your, Walmarts and other places. Going to be 175 and 125. So if I ask you, design an office building, you will consult these numbers, right? Every time you have offices, you're going to use 50. Lobbies, you're going to look at 100, correct? So example of live loads will be floor live loads, as we mentioned in this table. In bridges, what kind of live load we have? We have trucks and cars, right? So there are different type of live loads for bridges. Also for bridges, because of the impact that have, because of the braking force or deceleration, you will have some impact on your structures. You also have different type of live loads for every different type of structures. If you consult ABC International Building Code section 607.5 and 0.10.12, there is actually provision telling you that in your office building and any other building where partition, as we mentioned, location are subject to change. So you can change partition from location to another, because the office building, you are repurposing your office. Additional provision for weight of partition shall be made, whether or not partition are shown in your construction document. So if you have a construction document, if someone is including partition or not, you should include partition unless specified live load is more than 80 or greater. So if your live load is greater than 80, it is not you should not include it. If it's less than 80 PSF, you should include partition load of 15 PSF. So for example, if I ask you, you have an office building and you design for offices, what is your live load? Any numbers? 50, correct? Is 50 less than 80? Yes. So you need to use 50 for live load plus 15 for partitions. If I ask you to design a warehouse, storage warehouse, light, This number is 125. 125 live load is more than 80, so you don't need to include the partitions. Okay. Any question related to the partition loads? Okay. We also have what's called heavy loads. The code allows you, even after you select those numbers, like the 40 or 100 or 50 from this table, to somehow reduce them. It's called live load reduction factor. We will, next slide, know why we do that, right? But if your load is more than 100 PSF, you should not reduce your live load. So after you get, let's say you get 50 plus 15, and now your load is less than 100, you are allowed to reduce that load. But if your load is 125 or 250, you should not reduce it. So this provision say it called live load reduction. Yeah, hi, Adam. Yeah, go ahead.
Can you go back one?
Yeah.
So if it's like 75
Okay.
PSF and you
Okay.
add the 15 and it goes
Okay.
over,
So if you're 75, your live load is what? 75, right?
yeah,
It's more than 80 or not?
it's less.
It's less, right?
Uh-huh.
So what you should do is you add 15 to it.
Okay.
So it's gonna be 75 live load plus 15 partition.
Okay. So it doesn't matter that the total is over 80.
No, you don't do the totaling, right?
Gotcha. All right,
Okay.
thanks.
Any other questions? I like those. Raise your hand. Like in class, I will always have these interactions, face to face. So please raise your hand if you have any questions. Stop me and ask me to go back or slow down. So the next one is live load reduction factors. The code allows you to reduce the live load. Can someone tell me why the code could even allow you to reduce the live load? Anyone? Mike, Taylor, Juliano. Okay, who's this? Mike?
Yeah. Can you hear me now?
Yes.
Okay, good. Thank you. Is it because it makes the design process easier?
Not really, but imagine if I have 6-story building, right? And I have live load of 50 pounds per square feet, right? In all the floors. What is the probability of this happening actually?
Not high.
Right? If you have every story in your building, you made sure that every 1 foot by 1 foot is 50 pounds. Is it gonna be, unless you have like a 1,000 people party in the building, right? It's not gonna be, high probability to happen, right?
Yeah,
So
no.
the code don't want you to over design stuff because also you need to consider economy.
Right, right.
So there is some rules that allows you to go and reduce your reduction factor, okay? And do reduction factor for live loads. So is good, Mike, right?
Yeah.
Yeah, you got it.
Yeah.
So the code IBC allow you that can be used to obtain reduced live loads for members that support area KLL 80 more than 400. What is KLL times 80? If this is more than 400 feet square, so it's basically area, right? Because area is feet square, right? So KLL, it's called live load element factor. Live load element factor KLL is actually function of your element and element location. So if you have interior column, your KLL is what? Is 4. If you have exterior columns, without cantilever slab, it's 4. We have H column with cantilever slab, it's 3. We have corner column with cantilever slab, it's 2. If you have interior beam is 2, edge beam without cantilever is 2, anything else is 1. So let's draw a sketch. Let's say you have this is a plan view, right, of a building. This building is, you have column here, column there, column there, column here, column here. So you have 3 columns in this line, and also we have, oh my God, this is tough. So we have 3 lines, 3 columns in each direction. And you have to have beam connecting those columns, right? And you have a slab, cantilever slab, like a balcony on the side, right? So let's check KLL values. If I ask you for interior column, this is interior column, right? What is going to be your KLL? 4, right? If you have exterior column without cantilever, those are all exterior column without cantilever, this column, and this column. You also KLL is 4. If I ask maybe Chris, for this corner column, okay, what's going to be your KLL? This is a corner column, right? This is a cantilever, right? So it would be what?
2.
Yes, corner column with cantilever is 2, right? What about each column? This is each column with cantilever, right?
That one should be 3.
Yes. What about interior beam? Maybe someone else. Brandon, sorry. Or Liza.
It'll be 2.
Yeah, so if you have a interior beam, it is 2. If it's edge beam without cantilever, which is this one, it's gonna be also 2. Everything else is gonna be 1. So you already know how to get this KLL, right? What is AT is called area tributary or tributary area. We will note from the next slide what is tributary area. So tributary area is what each element serves. Like for this column, right? This is your structure, let's say. Those are the columns. So this column will carry half the distance from the left, half from the right at each span, right? So it's going to be half L3, half L2 in this direction, and half LA and half LB in this direction, right? So this is going to be your area, LA, half LA, half LA plus LB, so, and have L2 and L3. And this area will actually be carried by this column. And this is what's called AT, tributary area. Okay. In this case, for example, this column here will carry half LA and half L1, right? Also, you can apply it for the beam. So once you have AT and KLL values, because you know all those dimensions, you multiply them. If they are more than 400, you are allowed to reduce the original live load L1 by this factor. And this factor is 0.25 plus 15 square root of KLL AT. Okay? So can someone tell me if KLL is, let's say 4, and 80, let's say it's 300. KLL times 80 is 1200. It's more than KLL 8400. So you actually are allowed to reduce. So this number will be what? 1200. Can someone calculate this for me? Like 15 divided by square root of 1200 plus 0.22.
0.683.
Okay, so you are allowed to take 0.6. What did you say? 0.683,
0.683.
right? So you are allowed to use the original live load of whatever 50 BSF or whatever times this factor. So you reduce it almost by 31% or more, right? And that could actually result in very successful design. Okay. This is just a summary again of live load reduction factor. A member supporting large tributary area is less likely to be loaded at all points by the maximum live load. This is what we explained, right? What's probability of having this area with those people or this live load all the time? So you can reduce. And the equation is KLL 80 more than 400, you reduce it by this factor. And definition here, AT is a tributary area and KLL is live load element factor. But there is also upper bound. You cannot reduce much, right? You cannot say like, I'm gonna only use 10% of the live load. So there is upper bound for reduction that you cannot reduce than 40%, sorry, 50% if the member is supporting one floor, okay? Beam support usually one floor, right? Column support multiple floors, except of the last column, right? Before the roof, it supports only one. So for example, if you have, this is your floors, right? And this is your vertical column, correct? Sorry for this bad drawing here. So this beam here, right, carry the load for any live load above it here, right? So it's only from one floor. This column carry the load from one floor, so it can be considered carry from one floor. But this column actually carry load from this floor, this floor, this floor, this floor, so multiple floors, right? So there is also upper bound for your reduction here, okay? Any questions? So I can ask you in the homework, you are designing office building, right? So you get the number from office building as from here, 50. And I give you some tributary areas to calculate and some location of the columns, for example. And I tell you this is maybe carry one floor. You can calculate the reduction factor and give me the reduced load, right? Any questions so far? Anyone raising hand here? Okay, so with the, this is for what we mentioned is for everything except if you have roof, right? You notice that all our houses or some buildings, we always have what? Inclined roof, right? You know why we design for inclined roof? This, you guys have to know why we design your houses for inclined roof, right? So anyone can volunteer?
I'm gonna say ease of water flow and precipitation.
True. One of them is you don't need to, when it rains, actually, it's kind of easy to drain it, right?
And also triangles are the strongest shape.
Okay. Something else happened yesterday and day before, right? If you have a flat,
For snow.
yeah, what's gonna happen to your snow? Your snow will build up, right? If you have a buildup of snow, the loads on the floor in the roof will be high, right? That's why we build on the slope, try to just as much possible reduce the loads by having this inclination, okay? The reduction factors, okay, for the roof is live load for roof is the original live load, which you can use as 20 PSF if it's not given, times R1, reduction factor 1, R2. R1 is a function of the tributary area. Remember the tributary area we mentioned? If you have tributary area less than 200, in this case, you don't reduce because it's too little area to reduce. If it's more than 600, you use 0.6. If it's between, use this equation, 1.2 minus 0.018 tributary. And if you want to try to put 200 here, it will get you 1. If you put 600 here, again, it will get you 0.6, okay? So if I have a roof and I give you the tributary area, or you calculate the tributary area, you can calculate R1, okay? R2 is related to the slope of your roof, right? If your roof is inclined, for every 1 foot, you will have a rise, what's called the rise delta or F. So let's say your roof is sloped, every 1 foot is 12 inches, and you rise for 3 inches or 4 inches. So F value is 3. F is number of inches of rise per foot of a sloped roof. So if you have 12 inches here and you rise 3 inches, your F is 3. So in this case, is if F is less than 4, you don't want to reduce. If it's more than 12, you reduce to 0.6. If it's between 4 and 12, use 1.2 minus 0.05 F, okay? And I mentioned this is for live load, right? Live load means someone is climbing your roof. It's not the snow. It's the roof is inclined to have drainage, no accumulation of snow, etc. But some people can go up to the roof and put solar panels or fix stuff, right? So that's why the live load can be reduced. That's why we have inclined, more like a steeper slope, mean that no more people will be on your floor. That's why you can reduce more, right? So after you get R1 and R2, you multiply them, multiply by the original roof load, you get your roof reduced. Okay, any questions? If not, we will move to next type of loads. The other type of loads are environmental loads, which what we experienced. This is a diagram of house. You can see here sloped roof. You can have snow accumulation. You can have dead load of the roof. You also have wind days. You have live loads, people or furniture. You may have a storage or stored water tank. You may have soil pressure and weight of the walls and dead load. So this is a diagram for a typical load on a structures or house. So the snow load is environmental load that is depend on where you are, is geographically dependent, right? And varies. It's important to design for snow at cold state, and it's almost equivalent that you have 0.5 PSF per inch of snow, okay? So remember that in order to get the snow, if you are located in Florida, most likely you will not design for snow, right? But if you are in Alaska or here, you have to design for snow loading, correct? And it's very important to do because it's a really heavy load that goes to your structure. You also have rain, what's considered as gravity load. The rain is a water on a flat accumulate faster than in the slope. There is a section in or chapter 8 in ASCE provide information. We will not worry about the rain loads today or in this class, but we may consider snow loads. in our project for design. In order to get also the different type of environmental load, you have wind loads, okay? Wind loads is also based where you are located. Some areas have high wind, some areas low wind. If you are near the shore, you always have the storm surge. So you near the shore, your wind speed is higher. I want to tell you, actually, there is two tools here that you can get some information about your loads, environmental loads. If I skip here, if I go back to my website, the two websites here, the first one is ATC hazard location. What you can do here is you put your zip code or your address, let's say Rowan 08028 Glassboro, right? It gives you where we are in the map, and it gives you the wind speeds, right? The snow load that you need to use based on AC 716, 710, 75. The number 7 is the code number, and the number 16 is a year. So this is 2016, 2010, 2016, 2010, 2005. And the loads are 20 pounds per square feet on the ground for the snow. You also may get tornado loads, speed of 160 if you want to design for tornado. If you go back to wind speed, you will see, for example, AC 716, you will have what's called returned speed, which is 10 years, that the speed that return every 10 years, 76 mile per hour. Every 100 years you go up, you may experience 96 mile per hour. So this is more like probabilistic approach. We're saying, okay, every 100 years, you may experience 96 mile per hour. And every 10 years, you may experience 76 mile per hour. There is also what's called risk categories. Risk category 1, 2, 3, 4. Risk category is related to the building and functionality of your building. So the higher risk category, as you can see here, the higher the speed that you need to design for. Can someone guess for me what are the risk category for buildings? I know most of you don't know, but if you have a farm and you have maybe a building that doesn't have any human in it, right? So the risk to human life and safety is very low. So it can be considered as risks category 1, okay? So there is something happen, no one gets hurt, no one get killed. So this is category 1. Category 4 is anything essential. Essentials mean fire department, police station that is needed during any disaster. Hospitals, right? So we design hospital higher speed than the regular structures, okay? So the category 1 is no human presence. Category 4 is more of essential structures, fire department, police stations, hospital, etc. Category 3 is any building that will have difficulty to human to leave it. So for example, if you have nursing home, right? If you have a stadium where you got high wind speed or earthquakes and you need to evacuate, it's going to be hard for people to know where to go. So this is risk category 3. Risk category 2 is anything else. Okay, so category 1 is no human presence almost. Category 4 is essential building for recovery, so police station fires. 3 is if occupancies occupants or people in the building have difficulty leaving it. So for example, nursing homes or stadium or cinema or concerts. And risk category 2 is anything else, okay? You also are able to find the seismic loads. So we will discuss seismic in very short, in 2-3 minutes. You choose your code. You check where is your risk category. If you are regular building, maybe 2. Silent class mean that if you are in sand soil or rock soil or clay, the response of the building will be different because a softer soil react differently with earthquakes than hard soil. So if you, for example, if you assume C or D, you're able to get what's so-called response spectrum, which we will not cover much in this class, but this is just for your information how to get it. There is also another website for hazard map by ASCE. You also put your, for example, zip code, you search, it located for you. You here select your code. You can see here ASCE 722. You select your risk category, the soil type, and you can press, for example, seismic, view results. I show you the seismic result. If you go back and try to see the wind, it will show you based on your risk category, your wind speed should be 129 mile per hour to design for. If you need to know the ice or snow, it gives you also the snow value that you need to use, 46 pound per feet square. Those are always updated because climate is changing, and every 6 years this provision changes. Any questions so far? I would like you guys to go and maybe open those 2 websites and just try to play where your house is with your zip code and see what categories you are. After you get the speed of the wind, there is equation in ASCE 722 that give you, based on your height of the structure and the wind speed, give you the forces on the structures. The last environmental load could be earthquakes. Some areas is low seismicity, some area is high seismicity. Is Mike still here? Mike Waldron.
Yes, I'm here.
You took with me last semester the seismic clinic, right?
Yes, I did.
And we mentioned a lot that we have some system to protect for seismic, right? Like braces system and etc. So for the seismic, we have the ground to shake. So it moves, and this movement it varies with time. So you create velocity and acceleration. And since we have a building, which is a mass, if you remember your equation, let me put it in. Force equal what? Mass time acceleration, correct?
Yes.
So if you have force, if you have any dynamic system, mass time acceleration, right?
Yes.
Is your force. So if the movement, soil moves or ground moves in displacement, it can generate acceleration in your structure, right? And this structure has mass. It's not a light structure. So you will have mass time acceleration and give you forces in your structures. So it's a load is considered to be a certain geographic location. If you are in the West Coast or some region in the US, you'll have high seismicity. So we design for that. The more structure mass, the more forces. That's clear because force is mass time acceleration. Seismic event does not exactly cause loading, but cause acceleration. But acceleration and mass generate forces. A seismic force depend on the structure importance. If it's high, important, or low, as we mentioned, risk categories. It's possible to determine the seismic equivalent load by determining the horizontal acceleration and treat your structure as cantilever. So let's say this is your building, right? And this is your floor, and you have multiple floors. correct? And maybe have members, the diagonal members, right? So this is actually, if you turn this 90 degree, it looks like a truss cantilever, right? Where you will have force of the seismic force distributed over the height, and you can solve this building as a cantilever or truss cantilever to get the forces on the diagonals. Any questions so far before, I think we may have like few minutes. Any question in general? Any questions? So I will, since the next topic will need more than 5 minutes, I'll just ask you guys to just hold for 5 minutes. I want to take some notes on the attendance. And we can adjourn at 10:15. Okay. So I have here your spreadsheet for the list. Is student number 1 here? Is Tribunina? I'm sharing the wrong screen, right? So everyone can see their name, your name, guys, here, right? Student number 1 is here.
Yeah.
I'm here.
Yeah, just if you're here, just raise your hand. Okay. Let's see. Yeah, it's here. Okay, so I saw you here. Okay, so Liza is here.
Yes, I'm here.
Okay, Nick is here. Nick D.
I'm here.
Julia is here. I saw her, right? Julia's here.
I'm here.
Brad is here. Vlad is here. I didn't see Vlad. So Vlad is not here. Kathleen is here, right? Kathleen here. Yes.
I'm here.
Okay. Nick is here.
Yeah, that's me.
Okay. Julian is here too, right? Sean is here, right? He was here earlier. I don't know if he's still here or not. I think he was here. Python is here. Mike is here, right?
Yeah, I'm here.
Okay. Joseph is here, right?
Yeah, I'm here.
Tyler is here.
Yes, I'm here.
Kylan is here. Right?
Yes.
Kylan, yes, okay. Zach is here.
Here.
Andrew is here. Lucas here.
Yeah,
Yes, present.
I'm here too.
Well, yeah, I saw. Yeah, Ryan is here.
I'm here.
Okay, Julian is here, right?
I'm here.
Chris is here. Rob is here. Philip is here. Rob, I saw it. When I ask you guys, I remember the name. So Colton is here, right?
I'm here.
Okay. Mike is here. Mike is also here. Adam is here, right? And is Vivian is here too?
I'm here.
Okay,
Here.
and okay, so almost Vlad is the one that was not able to make it. Okay, guys, this is all I have for you today. Do you have any question before we adjourn? Any even general questions? Okay, if not, I will meet with you guys hopefully in person on Monday, 11 a.m. at Engineering Hall 320. And have a good rest of your day and stay safe and drive safe if you have classes on campus at 11. Thank you, guys.
Thanks. Have a good day.
Thank you.
Thank you. Have a
Thank
good
you.
one.
Thank you.
Good day.
Take care.